write it out. No, I mean not the math, the writing out. I'd rather do that.
Hello and welcome back to Calculus 2. 9.3 Tyler series. That's it. Tyler series, no one else? Taylor series. All right, good. Yeah, Tyrone series. All right, whatever. So, yeah, we have Taylor series here, and guys, we already defined everything in 9.1, so we're just going to copy that and I guess do another problem and be done. So, the Taylor series are defined as f of x is going to be summation of counter starts, let's call the counter n, starts at 0 to infinity. Then we have our coefficients ck that are given by the nth derivative computed at value a divided by n factorial times x minus a raised to the n. So this is your Taylor series definition, right? We have our coefficients over here, and these coefficients are in most of our previous lectures called Cn or Ck, right? So that's that. So now, when you have a power series, last time we said that you can expand sine x. And if you expand sine x using Taylor series, you get x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus dot, dot, dot going forever. And we've seen that as you are adding these terms, if we go through x to the 9, which is first 5 terms of this infinite polynomial, if you only use first 5 terms, you see that you can approximate values for the entire period of sine. From negative pi to pi, you can approximate any of those values using this polynomial with great precision. And that is really insane and nice. We also seen our ln x, right? So this was centered at x equals 0. Now, we also did ln x expansion last time, if I remember, right? And what did we have for ln x? For ln x, he was x minus 1, okay? So it was x minus 1 plus x minus 1. Oh, no, there was the one half in front. It's easier, better. 1/2, and then x minus 1 squared. I think it was alternating as well. Was this a minus here? Yes? 1/3 x minus 1 to the 3, and then it will be a minus, and then you put 1/4 to the 4, and so on. Now, this was centered around x equals to 1. You cannot expand your ln function around 0 because there is a vertical asymptote at 0, so you can't expand around vertical asymptotes. So that's why we expanded this around 1. Now also you have to be very careful, and I said this yesterday, if you are computing a value, right, if you need to do this to compute a value and the value is 13.5, well, expanding around 1 is a very bad idea, right? You actually, if you need to compute 13.5, then you expand around 13 because the value you are calculating is 13.5. So, or you can do 14, right? Something is close. So, let's take a look at one of the, oh no, so now I need to talk about the Maclaurin series. So, Maclaurin series are actually Taylor series with expanded around 0. So they just have a special name. So the sine x I did up there, that's a Maclaurin series because it's centered at 0. The one on the bottom that is centered around 1 is called the Taylor series. Now they're all Taylor series. Maclaurin is just a special case. Just like square is a special case of a rectangle, or a circle is a special case of ellipse, right? Where all radii are the same. Ellipse has two different radii, A and B, right? And they are different length, which is why it's oval. For circle, every single radius you draw is the same length, so it's a circle. And now you have the square and the rectangle. They are all 90 degrees, 4 sides, 4 angles, all of that good stuff. But square is special because it has all sides to be the same. Equilateral triangle and so on. So now we have the same thing, you know, happening here. We go, so if I want to, so this is just a special name for a special case. If you are expanding around 0, you can call it Maclaurin series. If you call it Taylor series, it's still fine, right? But see, if you call it Taylor series, then you have to specify that you are expanding around 0. See that? But if you have a Maclaurin series, you know the expansion is around 0. So if you say the name, right, then you don't have to have additional piece of information because it's encoded in the name. So Maclaurin series, right? Maclaurin series is a Taylor series expanded at 0. X equals 0. I always forget to check, but I want to see actually the historical fact on this. The reason why I believe we have Maclaurin series as a name is I think that Maclaurin was the first to find the expansion. And then Taylor did the general expansion, said, oh, but you can expand around anything, not just 0, right? So, you know, it could be that because it's really not that significant. You just expand around 0. You have functions that, right, the ln x, you can't even expand around 0. So it's not that special. But it is what it is. So Maclaurin series have the same procedure as this, and the remainder, again, is the next term. So for here, let's go with the blue. N plus 1 a over n plus 1 factorial x minus a to the n plus 1. So that just says compute the next term. Most of the error will be focused in that anyway. Oh, now it's Rn of x. Great. So you can watch yesterday's video again to see how those graphs work and as you're adding.
What's the notation of the numerator?
The fn plus 1, that's the derivatives. Calculated at value a.
Oh.
So this is, these are derivatives. So you go f prime, f double prime, f triple prime with the little tick marks. But then the fourth derivative is 4 in parentheses. Fifth derivative is 5 in parentheses.
Oh.
So the notation changes for derivatives because if you have to take a 7th derivative and you go 7 tick marks, and then you have to take a look and you still start counting tick marks, and a paper comes in with an imperfection with a little dot there, so you know what I mean, right? So we have the notation for more than 3 tick marks. We just use the derivative in the parenthesis. Those of you who would like to do some mathematical gymnastics between the course and the start of the next course in those 2 weeks, look up taking half derivatives and those kind of things. So we said 0th derivative is function itself, and then you have first and the second and so on derivatives. What does it mean to take a half a derivative, right? So, yeah, research it, find it. It's cool stuff, but it's not a part of the course, so yeah. Now we're going to switch to chart of Taylor series. So Taylor series are all worked out for you for basic functions for your memorizing pleasure, if you want to, or you can just ignore it and derive it every time you need it. Now, when you look at this list, right, you go, ooh, too many. Well, if you take a look at them, most of them are actually the same. And if you use a little bit of that, mental faculty that you have, you can figure out. So, yeah, I understand that the first ones, you actually don't have to memorize the power series. You have to memorize what made it. So if you just say 1 plus x squared plus x cubed, where is that coming from? It's coming from 1 over 1 minus x. And now if you alternate the terms, the sign changes. Now that is going to prevail with the rest of the stuff. You change the signs, you get the alternation. So we'll see how that goes. Now, again, those we generally don't see. I think that it's part of your lab, but we generally don't see them. Here are the e's and sines and hyperbolic signs. Those things are everywhere, right? Now, if you take a look at e, you have your 1 plus x squared over 2 factorial. So all are featured. It goes 0, right? X to the 0 is 1. So 0, 1, 2, 3, 4, 5, 6, 7. So all of the exponents in order, starting from 0, are there for e to the x. Now, what we know is that sine hyperbolic and cosine hyperbolic are made out of e to the x's. So if you take a look at sine and cosine hyperbolic, and if you are to add these two, you would get that. Now, I would say that common sense, but then it might not be common sense for you. Now, we also exercise the notion of even and odd. Sine hyperbolic, odd, so it's going to pick up all of the odd exponents, and cosine hyperbolic is even, it's going to pick up only the even ones. So sine hyperbolic and cosine hyperbolic are written in the language of e's, and that's why the power series between the two are the way they are. And now when you have the e, and you know the sine hyperbolic and the cosine hyperbolic, and you can split e into those two, then you say, well, what's happening with sine and cosine? Well, sine and cosine also bring some of the complex values, so they're not exactly e. But if you look at sine hyperbolic and the cosine hyperbolic, you see that the only difference is the sign alternation. Right? The sign alters. So stare at the sine and sine hyperbolic expansions. They're the same, except the sign alternates for sine, and it does not alternate for sine hyperbolic. Now, why is that? Well, that's due to the fact that you have number 1 in sine hyperbolic, and you have I in sine. And I is the square root of -1, and 1 is the square root of +1. So there's your positive and -1 situation that we discussed earlier. When you have +1, -1, you get alternation or you don't get alternation. So that's that's that. It depends on how vicious you are and how knowledge thirsty you are to remember these. As a student, right? So I obviously knew, and most of the faculty expects you to know e to the x at any given point. Now, as soon as you know e to the x, you can split into these two and then give them sign alterations to get these two. So it's very simple to get through these things. And then the difference between e to the x and the puppies up there is that this is divided by dn factorial and this one is not. So if you start from there, you can go into e to the x splits into sine hyperbolic, cosine hyperbolic. You put the sign alternation, you have your sine and cosine. So you learn 7 of these like nothing. Now, do you have to memorize them? No, you don't have to memorize them, because you can you always get them by working out the procedure and then work out 3 or 4 or 5 derivatives, and and you have. Now, so obviously, it's very convenient to know what they are. So now they are asking us to expand sine of 3x. Expand sine of 3x. Well, I start by saying that expansion for sine x, we know it, is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus dot dot going forever. And then in the next step, you know, because you studied the properties of power series, that you can replace x with 3x. And as soon as you do that, you have your x is now 3x minus 3x cubed over 3 factorial plus 3x to the 5th over 5 factorial minus 3x to the 7th over 7 factorial plus dot 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 going forever. So each one of these parentheses houses 3x. So you are taking your sine x, right? You are taking your sine x and you're just replacing every x with a 3x. So if you need to expand sine 3x, you expand sine and then you replace each argument of x with 3x. So you are replacing in your power series every x with 3x. That's the function composition we talked about earlier. What is cosine hyperbolic? They say 3x again. Cosine hyperbolic. So we have expand cosine hyperbolic. Let's go 6x, whatever. Well, you start with the cosine hyperbolic expansion. Now, sine and cosine hyperbolics do not have sign alternation. So, and we just have even ones for this, right? So we have 1 plus x squared over 2 factorial plus x to the 4 over 4 factorial plus x to the 6 over 6 factorial plus dot dot dot. It will go forever. So cosine hyperbolic has all pluses. Cosine x will have plus minus plus minus plus minus sign alternation. So now to come up with a cosine hyperbolic of 6x, we are going to just replace all of our x's from hyperbolic cosine with 6x. So I have 1 plus 6x squared over 2 factorial plus 6x to the 4th over 4 factorial plus 6x to the 6th over 6 factorial plus dot dot dot. And I just fill in the 6x everywhere. You have a polynomial, guys. And you decide how many terms you want to keep, right? Again, precision versus the amount of time spent calculating and computing. So that's your job. That's the Taylor polynomial, and as I said, Maclaurin polynomial. By the way, all of these were Maclaurin because you just have x. If it was a Taylor polynomial with, like, let's say expanded at 2, each one of these would be x minus 2, right? Squared x minus 2 to the 4th and so on. And then you're replacing the 6x in. Good. That's that. Bye.